Thank you so much for purchasing this exclusive content. By purchasing this exclusive content, you are making it possible for us to provide more free and exclusive content. We work very, very hard to bring you these videos. The videos take many, many hours to produce and to research, so I hope you enjoy and benefit from these videos. So the first thing we should do is write a program to test these two LEDs to make sure they're working. We'll do a blinking on both of them. Okay, let's go into Atmel Studio, create a new project, and select the microcontroller. Okay, we have our default starter code. Let's do the data direction for port D. One, two, three, four, five, six, seven, eight. Okay, so it's the number 2 and number 3 that we want to have an output. Port D, port D, and then I'm going to turn one on and one off, and then I'm going to toggle each one so they blink alternately. So I'll turn number 2 on, and then I'll have number 3 off. So in the loop, we're going to need the delay on this one. And I'm delaying just so I can see them blink. We'll do 1/4 of a second. And then I'll toggle each of the LEDs. Pin D2, and do the same thing with the third pin, or pin D3. Okay, let's build this and see if we get any errors. 0 errors, 1 warning, and that was the FCPU not defined. So that's good. So we can go ahead and program the microcontroller. Okay, the controller was programmed, but you can see that only the red LED is toggling and the green LED is not. So let's see what kind of problem that could have arisen. Okay, coming back to the program, it looks like I didn't write the decimal or the binary correctly. And I was considering this as 1. The first digit here as a 1 and not a 0. Indexed from 0, not indexed from 1. So this is actually 0, this is 1, this is 2. And the pin 1 and 2 is not what I'm wanting. I wanted to use the pin 2 and pin 3. So this is pin 0, pin 1, pin 2 and 3 is going to be output. Now this one is also incorrect because I'm not using pin 1. So I need to make that a 0, and I'll go to pin 1 and turn that one on, or bring that high. So I got 0, 1, 2. And these should be correct, so let's do another build and program. Okay, so the LEDs are working correctly, so now we can go on and continue with the programming. Now that we have our LEDs working, let's go ahead and write some pseudocode to start establishing some communications. Outside of the while loop, we'll need to initialize I2C. We're not going to need this information anymore, but we will use this in an error loop. So I'm going to go ahead and create a function up here for error. This is where we'll be going when there's a status error where we're not expecting a particular status value, and it will go here when that is found. I'm just going to take this and copy them or drag them over, and we can have them here just in case we need them. We won't be using them yet, but we will be shortly. The communication for looking or getting the device ID, which is just reading one register on the accelerometer, we really don't need to have this in the while loop because we're not constantly getting information. We're just trying to get one piece of information. So we're going to do that outside of the while loop. So we'll make some space. We know we need a start condition. and we need an end condition, or stop condition. We know that we're going to need to read, or actually get the correct device, so we're going to have to send a slave, or send the slave address. And we don't know what we need to do yet for the writing and reading, so we'll just leave that unknown at this point. Now would be a good time to take a look at the datasheet for the device, for the ADXL345. So let's take a look at the datasheet. You can get the datasheet from nlog.com, or just Google ADXL345 and you'll find the datasheet near the top of the search. So we're going to go down to the I2C portion, which is on page 18. And this is all the information we'll need to know to do what we need to do. And over here it shows how we need to communicate with the device. We have the single byte write. We're not going to be writing single byte, we're going to be reading. Multiple byte write. We're not going to be writing multiple bytes, writing or anything writing. It has a single byte read and a multiple byte read. We're only going to look at one byte, which is the ID. You'll have to scroll down to the register map to find out what you need to find, or what you need to use to find what values. So we have the device ID on the register 0x00 in hex. So that's the register we need to access the device ID. So now we know that, we can go back to looking at how we communicate. Okay, so it's single byte read. That's the one I think we should select. We're not going to do multiple byte read. And it looks like it shows the master and slave what is expected of these two devices. The master is what is expected from the master, and what is expected from the slave. So it looks like we have to do a start. We've already established that in pseudocode. And the slave address write. Now you must be wondering why we need to do a write when we're just looking or wanting to read an address. But we're writing to a register address, and then we're going to do a restart to do all the read. So it looks like that we need to first write a register address, and then we need to do a restart, and then do a slave address read operation, and then start reading the data. On the multiple byte read, you can see it does the same thing. You have to write to the address, and then you do a restart, you do another read, and then you start reading data one byte at a time. So let's see if I can put this in half the page here so I can see it. Okay, so we have the start, and then it looks like we have to do a slave address plus a write. We're going to expect an ACK from the slave. Then we are going to write the register address. And then we're going to receive a slave ACK again. And then we're going to do a repeat start. And now we're going to do the send slave address and read. And then slave will ACK again. And we receive data. Should say slave. Well, it shows that the slave is showing data here. That just means we need to pick it up. So I'm just going to put in read data. And it looks like we have to deliver the NAC because we're only getting 1 byte of data. If we were getting multiple bytes, we would just put an ACK here, read another byte, and then do a NAC, or read another byte until we do read another byte, ACK, and then keep doing that until we have the last byte, and then we do a NAC. So we do a master NAC, and then we do a stop. So now we have our pseudocode. We can start putting in code, real code. First thing we need to do is make sure the power reduction register, you can see that has the 0 at the end. The bit that controls the 2-wire interface power reduction. And we want to make sure that that's not set, so we want to make sure that is a 0. So we're going to use our AND NOT bitwise operation. We do this type of operation because we don't want to affect any other bits that are within this register. So we do it this way, so we only affect that single bit. Since we're polling, we want to make sure that the interrupt enable is not set. That's under the control register for the two-wire interface. In the previous video, we stated that the TWBR, the bit rate, would equal 2. Since I'm working with a 1 megahertz clock, and I'm going to be establishing a 50 kilohertz clock for the I2C. And we need to make sure that the two-wire status register, the bits that have to do with prescaling, is going to be 0. Might as well comment this stuff out so I know what's going on later on. For the start condition, we need to go to the control register, and we're just going to use the equals. We don't need to worry about any other bits on there because we're going to be really controlling this register and setting the bits that we need to set. So we need to set the TWEN, the TWINT, which is the flag, and the start bit. Now we need to wait for the flag to be set. When this flag is set, then that gives us the go-ahead to go on to the next instruction. And we know that this has been completed, at least on the master's end. Now we need to check our status register. If it's not equal to 0x08, then there should be a problem, or there is a problem. So we'll go to the error, I2C, two-wire interface function. Let's actually go to this function and make it actually do something. So I'm going to do a for loop. I think I'm going to have it blink for a certain amount of time. I'll make this 100 blinks, and it'll be toggling, so it'll actually light up 50 times. We'll use that green LED. We won't need the red LED, and we'll put a delay in there so we can actually see it blinking. And the delay, I'm going to make it around 20. I want it to be a pretty fast delay. So it's going to toggle the LED 100 times, which will show 50 blinks. I'm also going to add a delay at the end of this because if there are more than one errors in a row, I won't be able to see that. So I'll put 1 second in between, which is 1000 milliseconds. Alright, let's go back to the start condition, make a comment here. To ensure that it's actually working, I think I want to put an else in here. I'll go to another function. I'll create another function that's similar to the error, but I'll just have the LED on for a short amount of time. So I'll actually turn this pin on, which is just using the OR bitwise operation, and I will have it on for about half of a second, and then I'll have it turn off. I could just use a toggle here, but I want to make sure it's off. This is a bit of an OCD thing for me. Okay, let's continue, and we can use the past status check in the else. Now if we have an error here, we'll have that blinking. If we don't have an error, we'll just have the LED blink on and off once. This way we'll know which part it will or will not have an error. So since I'm going to have all of these, and I'm going to be checking for most of these actually, I'm going to see this past status check turn on for almost all of these operations. So I can actually count when I'm looking at the circuit board, when I'm looking at the circuit to see which one it failed. So let's say it's the third one down. This blinked on and off 3 times, but then it did a fast blinking. I will know which one it failed. So this is all we need to do with the start condition. We can go on and do the send slave address and write. As I mentioned in the previous videos, the slave address is going to be 3A, which is the slave address and write. So all we need to do is put that address within the TWDR register, and that's all. The contents will be just this, it won't be anything else, so I can just use the equals. And we need to clear the flag and enable. If all of these operations, the shifting operations and the ORs and all the stuff that you're seeing here, and you're looking at it like wondering what the heck that is, watch my previous videos on YouTube under the Microcontroller playlist, or check them out on the Newbie Hack website. Now we're going to do the same thing we did up here. We're going to wait for the flag to be set. So what we could do, I'm wondering if I should copy it to this location or just create a function. I'm thinking I'm going to create a function instead, because that will also be a way to reduce the errors that I may have. Because if I do a copy paste, or if I retype it every time, I may miss a not, or maybe one of these symbols here. So I'm going to go ahead and I'm going to refactor it. I'm going to create a method to do this. And I'm going to use the refactor function here, extract method, and I'm going to call it it's okay. So now we have that code within this function, and now all we have to do is add that here. We may actually add some more information in there, and I'm not really sure yet what to do, but we'll get there. I think I do want to create another function for just this, so I'm going to refactor this as well. And I'm going to call this check flag, status register. So now I'm checking the status register, but I want to pass in the actual value, the flag. So I'm going to call this an unsigned integer, 8-bit unsigned integer, and I'll call it status. And this one has 0x08 to be passed in. And in this case over here, we have to do the same thing. We're checking the status register, and it needs to be 18 in hex. And 18 means check the status register for the SLA, or the slave address, plus the write transmitted and ACK received. We may be able to put these two together, but I'm going to wait and see. Now we need to send the value of the register, And since this is already done here, the ACK is received, we can take that out. And what we need to do now is write the register, write the data, which is the register address. And we do that under the TWDR, the data register, and that's going to equal 0x30. Oh, no, not 30, 00. Because 00 is the location of the ID that we're going to be reading from the device. We need to do the same thing we have here as the next instruction because we're clearing the flag and enabling it. So let's go ahead and refactor this. Okay. Clearing the flag and enabling it. And then we're going to wait for the flag to be set. And then we'll check the flag. And the flag should be 0x28. And that is checking for data transmitted and ACK received. Now we know that that ACK is received. I'm keeping the comments in here because this is really the only thing that's changing. And I'm making these very verbose so I can know what it's actually doing. So this is almost a comment in itself. Okay, now we need to do a repeat start. It's going to be the same thing as this one, so let's go ahead and refactor this, and we'll just call this a start. I'm going to put an underscore there because it's a little bit easier to read. And I'm going to change these as well. Let's see if I can rename them under refactor. Yeah, we can do that. Okay. I'm going to do the underscore for all of them. Now it's more clear that there's an I2C involved. Alright. So the next thing I need to do is wait for the flag to be set. And as mentioned in the video, the status register will have to be a 0x10 for a restart. If we just put a 08 in here, it would error. It would show us the blinking lights because that is incorrect, and the status register will actually have a hex value of 10 instead. Now we need to send the slave address and read, and we're doing the same thing here, which is we're doing it with a write. So I'm going to go ahead and just take all this, and the write or the read is 3B rather than 3A. And this is going to have to change as well. And this is a 40, and that's for SLA or slave and read transmitted and ACK received. So we've received the ACK, we don't need to listen for that. Now we can read the data. And we also need to create a variable as well so we can store the data somewhere. So let's go ahead and create an unsigned integer. We'll call it ID from slave. Form slave from, I'll call it ADXL. I'll initialize it as well before I do that. And now I need to make that equal to the TW data register. I don't know why I had that in here like that. Let's see. It's weird. There we go. That's better. Now, I can go ahead and use the clear flag and enable because that is going to give me, that's going to push a NAC on the line. If I wanted to push an ACK so I can read more data, I'd have to add the TWEA additionally to this, and we'll take a look at that in another video. Actually, I'm going to create a function for it anyway because that would be good to have in the back pocket. So this would be, say, I2C, clear flag and enable with ACK. Okay, we're going to wait for the flag to be set. And the check register will need to be 58. And that is check for data transmitted and NAC sent. It's not data transmitted, it's data received. And NAC sent. Sending the confirmation that this is the last byte to be read. And now all we need to do is create a stop condition, which is the control register. And that is going to be equal to clearing the flag, the enable, and the stop. Okay, so we're finished with the programming. I can do a build and see if we have any errors. Save it first. And let's see what we got. Build. So I have 2 warnings. And it's the same one I get. So it looks like it should be fine. There's no errors, which is kind of strange. Makes me worry. But generally I don't usually get it right the first time, but we'll see. It looks like we got a warning here, and it looks like it's just informing us that we have a variable that has been set but never used. And that's not a big deal. I just want to see if I get through all of the steps without any errors, and I'm able to get to the past situation, pass the status check on each one of them. Okay, now I'm going to program the microcontroller, see what I got. Programmed successfully. The microcontroller is programmed, so let's see what happens when we plug it in. Looks like the LED stays on and then it turns off, so there's something wrong with the LED where I'm turning past the status register where it turns it on and then turns it off. So let's see what happened. So here's the past status check function. What I'm doing is I'm turning on the LED, waiting for 500 milliseconds, which is half of a second, and I'm turning it off. What I see happening is it turns it right back on because it goes through the next instruction. So I need to turn it, or I need to provide a time delay after it's turned off so I can see that it's turned off. So I'm going to use the 500 milliseconds, which is half of a second. It should be good. Let's go ahead and build it and program. Okay, let's try it again. Looks like we have blinking. I didn't count the number of blinks, so let's try that again. 1, 2, 3, 4, 5, 6, 7, 6. So it's 6 blinks. So let's check out how many times we're making it blink or checking the status in the program. Okay, let's go down here to see how we're doing this. Okay, we have a start, so that will have a blink. 2, 3, 4, 5, 6. Okay, looks like we were able to successfully communicate with the accelerometer on all 6 controls. So let's just to test to see if the error is working, because we didn't get any errors. Let's change one of them to a different number. Let's try 28. And let's see if we get an error on this one. Okay. Let's build it and then program. But just because we see the LEDs going and we don't have any errors and we're getting what we're expecting, we don't really know how to see the ID. I mean, we only have this red LED, which we'll be using later on with the accelerometer and dimming as we tilt. So I'm going to show this to you in the logic analyzer to show you that it actually is working. So I'm going to connect the logic analyzer to the SCL and SDA lines and on the ground, and then I'm going to show you the captured data for the logic analyzer and show you the data that is showing us for each communication. I'm going to use the logic analyzer by Saley. We sell this on newbiehack.com. I'm going to use the logic analyzer to watch the lines, the SCL and SDA lines. You can add an analyzer or protocol on the list of analyzers. You can add it, you can remove it as well. You can add an analyzer by pressing the plus, and you can pick one of the predefined analyzers. I'm using the I2C, and I'll use channel 0 is channel 0 here, channel 1 is here. So I have to make sure that I use the black and brown wires. Black for the SDA and brown for the SCL. And I'm going to use the 8-bit read-write bit included, and this is the default. The selections they have is the 8-bit read-write bit set as 0 or 7-bit address bits only. So if I select this one, I'll only see the address bits. I won't see the 8-bit portion of it. And this is only set as 0 if I select that one. So I'm going to keep the default, press save, and then I have that set here as the analyzer. When I run the analysis, or when I start, I'll see a list of the actual communication that's happening. And when I click on the list, I'll be able to expand it here. So I'll show you that when I do the analysis. The gray wire will go to the ground. Since the lead doesn't have a male header on it, I'm going to just connect a jumper to it, and I'll connect that one to ground. The black lead connects to the SDA. Not much space, but I'm going to use the same place where the resistor is using. And now we'll use the brown for the SCL. I'm going to do the same thing, plug it right where the resistor lead is. Alright. Everything is plugged in the way we want. We have the black wire going to the SDA, the brown wire going to SCL. I'm going to press the start, make sure that it is on a duration that will allow me to plug this thing in time. And the analyzers are set up correctly, so I'm going to go ahead and press start and plug the microcontroller in. Alright, so it looks like we got some communication on the right hand side here. This is what it actually sniffed out on the line. You'll see if I zoom out, we'll see the actual communication. The little blue mark here, that's a start. The little blue, or I'm sorry, this is a green dot. That signifies a start. This green one here signifies a restart, and the red one signifies a stop. And you'll notice that there's quite a bit of space in between here. And it says 1.007 seconds on each one of these. This one has 3 seconds, I'm not really sure why. Oh, you know what, I think I forgot to change the program to omit the error, but it doesn't really matter because it still goes on to the next instruction anyway. And then you have a 1 second here. So we had a blink on and off, then we had an error shown somewhere in here, or maybe this is just the whole error. So let's take a look at it individually. We did a start, and then we had a write, which was we did a start and we did a slave and a write. And that's the first one. We can double click it, take a look at the actual digital waveform. And then the next one we did is a register write, or a write instruction. And this is the 00 register. We can double click that one, it'll go to that location. And then we did a restart, which we won't see in here. We don't see the start, the restart, or the stop in here. So we can zoom out and take a look at what's next. You can see that the restart is next. So the read is the read, or the slave address and read is the next instruction that you see in this location here. And it's the value 3B, which is the slave 1D plus a read. And then we have the final value that is inside of the 00 register. And you can see that we also sent a NAC, so the instruction will be completed or ended. If we put an ACK here and we didn't put a stop, we could turn the, or actually I'm not really sure, it may make a difference if it's, I don't know if it's in the, if there is an EEPROM on the ADXL, but I have a feeling that there may be, because if you unplug it then plug it back in, it may still be waiting for another read. So you got to be careful with that, just in case the state machine is in a non-volatile state on the ADXL, which means that it's the program that's running on that actual chip is non-volatile memory, which won't be erased when you unplug it. So you want to make sure that you have a NAC and a stop at the end, so the complete instruction has completed entirely. So that is how you communicate using I2C or two-wire interface. I've shown you a basic method, showing you most of the commands that you'd use in I2C. In the next video, we're going to access more of this accelerometer, and you can expect to see that video on the same page. So if you've made a purchase to see this video, you will also see the next video once it's complete. Thank you very much for watching.